Hello students, and welcome to this, the 13th logic lecture of Comp 0003. Now, previously in the course, we've looked at propositional logic, which is simple. It's simple to reason about, but it's quite weak in terms of expressivity. And we've also seen first order logic, which is very powerful. I mean, in fact, you can do a very great deal of mathematics in first order logic, as we've seen. But it's also, it's so powerful in a way that it is quite difficult to kind of reason about, particularly in any kind of automatic way. And that's really important for computer science. So today we're going to begin our final main topic, which is modal logic. So modal logic sort of sits somewhere in between propositional logic and first order logic in terms of expressivity and also complexity. So essentially we start with propositional logic and we add two modalities, a sort of a box modality and a diamond modality. And box is supposed to be read as being sort of saying always or necessarily. And the diamond is read as being sometimes or possibly. So this seems like quite a simple extension, but it allows us to talk about different situations and different possibilities. And indeed, the semantics is often couched in terms of possible worlds. So you have some kind of set of possible worlds and ways of moving between those worlds. And the modalities in modal logic allow you to express properties about what happens at other worlds that are reachable from the current one. So I've said, I think many times, that logics have got two main components from the point of view of this course: a syntax explaining what counts as a formula, and a semantics which gives a meaning to the formulas. So today we're first going to look at the syntax of modal logic, and then as before I'll explain how we can render some natural English sentences as formulas of modal logic. Then I'll introduce the semantics of modal logic, and we'll do some examples. And we might finish with a little piece of reasoning in modal logic as well. So I think the last lecture was quite long and technical. I will try to make this lecture a bit shorter and hopefully a little bit more conceptual and less technical, to give you a bit of a break from all the hardcore logic and maths. So let's go and have a look at the slides first now, and let's look at the syntax of modal logic. So here on this slide, I've tried to give a very kind of high-level overview of modal logic. As I said already, modal logic is somehow somewhere in between propositional logic and first-order logic in terms of expressivity. From the syntactic point of view, we just start with propositional logic, and we introduce two new unary connectors, which are called modalities. And so the syntax is really not very much more complicated than propositional logic, and a lot less complicated than first order logic, because we don't have function symbols and terms and predicates and this kind of thing. The semantics, though, is quite a bit more complicated, because instead of just propositions being true or false, we have the idea that modal logic is talking about a set of possible situations, and we have the idea that a proposition could be true or false in any one of those situations or possible worlds. That's still a lot less expressive than first order logic, and the semantics is going to be a little bit like first order logic, but less complicated. I should also say that here we're just going to study one particular version of modal logic. There are, in fact, many different ones, and we can take lots of different kinds of modalities and ways of reading those modalities, but we're just going to use here the most common one that is in very widespread usage. And we're going to have two modalities which capture the notions of possibility and necessity. So let's go on and just, I'm going to not fiddle about too much and just give the syntax of formulas straight away. So I'm going to give our grammar for modal logic as follows. First of all, the atomic formulas, as in propositional logic, are just propositions. So any proposition letter, P, Q, R, and so on, is an atomic formula of modal logic. Then we have all our familiar connectives from propositional logic: negation, conjunction, disjunction, implication, and by implication. And then we have the two modalities. We have diamond A. So if A is a formula, then so is diamond A. And diamond A is read as it is possible that A, or possibly A. And we also have a second modality, which is represented by this box here. So if A is a formula, then so is box A. And box A is usually read as meaning it is necessary that A, or necessarily it is the case that A. So, I'm sorry, and just this little remark here. So P ranges over proposition letters, so any proposition is a formula. So one more notational note, I suppose, is that usually we consider the box and diamond modalities to have higher precedence than the binary connectives, so they bind tighter. So for example, if I write the formula box A and B without brackets, then what you think is that the brackets implicitly around box A, so it's box A and B, and not box with the brackets around the A and B. If we want to disambiguate, then we can always put the brackets back in. So let's immediately, without giving the kind of formal semantics of modal logic, let's have a go at translating some English sentences into modal logic. Just going by the intuitive idea that box A means necessarily A, and diamond A means possibly A. So the sentence is, it might rain later, and then again it might not. So again, the game, I think, really is first of all to identify the propositions, and then to identify both the connectives, but also the modalities. So I think the best way to think of this is the proposition. We take proposition R for it is raining. And so we can say that diamond R means it's possible that it will rain. And then we have a conjunction and it's possible that it won't rain. Possibly not R. So possibly R and possibly not R. So diamond R and diamond not R. It might rain and it might not. It's possible that it will, and it's possible that it won't. If you're in the pub, then you must have skipped class. So, okay, we can think of two propositions. P for you're in the pub, and S for you've skipped class. So this is a statement about something that is necessary. So if you're in the pub now, if P, then necessarily it is the case that you've skipped class. So I would choose to render this as the formula P implies box S. If P, then necessarily S. Oh, so I see that I've written C for skipped class and not S. That's the danger of not having read carefully enough beforehand. Next example. It must be possible for me to solve this problem. Now, I'm not going to second guess which proposition letter I might have chosen for I will solve the problem, but it says it must be possible. So if I was just saying it is possible for me to solve the problem, I would say possibly S, so diamond S. But I'm not just saying it must be possible. I'm not just saying it's possible, I'm saying it must be possible. So necessarily, it is possible that I can solve S. So it is necessarily the case that it is possibly the case that I will solve the problem. So this is a case where we have, I think, two modalities, box, diamond, S. Oh, there we are, and I guessed it right. Final example. Maybe my death is inevitable. I mean, that's an optimistic statement at the best of in the best of readings. But so we have maybe, which is obviously a state about something that something is possible, and saying that something is inevitable is to say that it is somehow necessary. So it is at least possible that it is necessary that I will die. So this is a case where, again, you have modalities, but the other way around. Diamond, possibly. Box, inevitably or necessarily. D for I will die. So this just goes to show you that just like quantification in first order logic, the order in which you write modalities really matters. Box diamond says something is necessarily possibly true, and then whereas diamond box means something is possibly necessarily true. So now I want to go on straight away and introduce the semantics for modal logic. Now, obviously, the main feature of modal logic that we don't already have in propositional logic is the modalities. And then, so we need to account somehow for the idea of possibility and necessity. Now, that means that obviously we can't think of propositions as just being as being always true or always false, but we have to think of them as being, possibly true or possibly false or necessarily true. And this gives rise to the idea of a kind of a frame, or sometimes called a Kripke model, named after Saul Kripke, who's a mathematician who's most prominent in the mid-20th century. And a frame is a pair, usually writing M, a pair W and R, where W is a non-empty set, and we usually think of those as it being a set of worlds or situations. So, they could be possible states of a computation, or they could be, possible universes in quantum theory, or really anything else, just any set. And R is a binary relation on W. So, in other words, R is a set of pairs of worlds. That's what a binary relation means. Of course, that means that, if you have a set of things and a binary relation on those things, well, that's actually exactly a directed graph. Directed in the sense that the order, the direction of edges matter. But so a frame, you can think of it this way, is a graph with vertices W and edges R. So that is one way of thinking about a frame. So this relation R is sometimes called the accessibility relation on worlds. So we have a notion of some worlds being accessible from others or not. And so we say that, so if we have that a pair, W and W prime of worlds, is in the relation R, then usually I'll just write that as R, W, W prime, because it's quicker. And we say that the world W prime is accessible from W. Now, in some cases, the relation R will be symmetric, which means that if W prime is accessible from W, then the reverse is always true. But in general, that's not true. So a frame is a set of possible worlds together with an accessibility relation, a binary relation on, say, telling you which worlds are accessible from which others. So that's our set of possible worlds. And then we have the idea of how do we assign a truth value to propositional formulas? Well, the idea is really that in modal logic, whether or not a proposition is true or not depends on which possible world you're in. A proposition will be true in some worlds and false in others. So let's suppose that we fixed some frame already, so we've chosen our set of possible worlds and our relation, our accessibility relation R. Then evaluation, instead of assigning just a truth value to propositions, it's going to tell us which propositions are true at which worlds in W. So if we write L for the set of all proposition letters, then, evaluation is then said to be a function from proposition letters to sets of worlds. Formally, it means that I'll write rho again for valuations, and it is a function, probably should have written this with like a little line there. I'll maybe correct that. A function from L into the power set of W. So it takes a proposition letter and returns a subset of W. So in other words, it returns a set of worlds. Another way that is completely equivalent to think about this is that you could think of valuations taking a proposition letter and a world and returning either 0 for false and true and 1 for true. But this is exactly the same thing, or it's equivalent. Given a proposition letter, P, row of P, tells you the set of worlds at which the proposition P is true. Okay, so on the board here, I've drawn an example of a modal logic frame and valuation, very roughly inspired by one of my favorite poems, which is The Raven by Edgar Allan Poe. In The Raven, it's basically our protagonist is harassed by a bird while mourning the loss of his dead wife, roughly speaking. The Simpsons did a great version of it sort of back in the 90s. I strongly recommend you look that up. But I mean, it kind of begins as follows. Once upon a midnight dreary, while I pondered weak and weary over many a quaint and curious volume of forgotten lore, while I nodded nearly napping, suddenly there came a tapping, as of someone gently rapping at my chamber door. "'Tis some visitor," I muttered, tapping at my chamber door. Only this and nothing more. So, so our protagonist, the narrator, starts off in his chair, and then he hears tapping, and he first of all investigates the door, and there's nothing there, and then he goes to the window, and then a kind of raven hops in, and then kind of sits on top of a bust on top of his door, and then kind of harasses him and won't leave, and he gets very kind of cross about it, and then depressed, and then terrified. So here is our modal logic frame, very roughly based on the first few stanzas of The Raven. Our set of worlds is given by three states, three possible worlds. We have the chair, we have the door, and we have the window. So those are our three worlds of the frame. And then I've drawn edges between them, which is supposed to kind of capture the notion of accessibility, just in the sense of physical accessibility. So in fact, all the edges here are bidirectional, and this is a case where you can reach every world from every other world, including itself. So, for example, from the chair, you can go from the chair to itself, or you can go to the door or to the window. So, for example, chair, window, and chair, door, and chair are all elements or edges, if you like, in our accessibility relation. And then I'm kind of thinking that there are propositions which are true or not at particular worlds. And I've written these in blue here. So I've chosen three propositions: N for I am napping, T for there is tapping, and R for there's a raven. So napping is true at the world chair and at no other worlds. So if you're at the door or the window, then you're definitely not napping. So I'm thinking of a valuation row where row applied to the proposition N for napping is just the set consisting of the single world chair. So row of N is just set chair. But then we have tapping that occurs both at the door and then later at the window. So here, row of T is the set door and window, and so two elements in that set, and we have raven, which is true only at window, although of course later on it does move to the door, but never mind about that. So in this valuation, row of R for raven is just the singleton set window. And we'll come back to this example in a little while. Next, we'll look at the satisfaction relation for modal logic, and then we'll come back and look at this example again in just a moment. So let's go back to the slides. So now, as we've done before for propositional logic and first order logic, Let's now give a satisfaction relation for modal logic. So I'm going to assume that we've already picked some frame M, which is worlds W and accessibility relation R. And I'm going to assume as well that we've picked a valuation rho to let us know which propositions are true at which worlds. And I'm going to write this small w to represent some world in the set big W. And then I'm going to write M and W satisfy with little rho A, this notation here, which involves the frame, the valuation, somehow W, which is like the current world, and a formula A, to mean the formula A is true at world W, and that's relative to the choice of the frame and valuation. So this is very similar to the first order logic notation, except that now we're somehow parameterizing by saying we're having a concept of which formulas are true at which worlds. So, I mean, as before, we're going to define this relation inductively on the structure of modal logic formulas. So, first of all, and most importantly, what does it mean for a proposition letter P to be true at world W? Well, we already have a valuation, this little rho, which says for every proposition letter which worlds it is true at. So remember that if I apply rho to the proposition P, I get back a set of worlds, a subset of big W, that is supposed to be the set of worlds intuitively at which the proposition P is true. So formula P is true at world W if and only if W is in the valuation of P. Then we have all the usual clauses for the propositional connectives, and I'm not going to give all of these because they're completely standard. So for example, the formula not A is true at world W, if and only if the formula A is not true at world W. So we don't do anything to the world or anything. We just invert the satisfaction relation. Similarly, the formula A and B is true at world W if and only if the formulas A and B are both true at world W. And the same for all the other propositional connectives, so it goes exactly the way that you think it's going to go. Now, let's think about the modalities. So first of all, the formula diamond A. Now, diamond A is supposed to mean it is possible that A. Possibility here, the way you interpret it in modal logic is you say there is, so possibly A is true at world W if there is some world accessible from the current one, so accessible from W, where A is true. Possibly A, or saying A is possibly true, means there's at least one possibility starting from now where A actually is true. So that is to say, there exists a world W prime such that W prime is accessible from W. So that's saying R W W prime. So, or you can, instead of accessible, you could also think of reachable, or reachable but in one step. And the formula A is true at the world W prime. So diamond A means there is some accessible world from the current one where A is true. Now, the interpretation of box is somehow dual to that. So necessarily A somehow is interpreted in modal logic as meaning in all possible worlds, no matter which possible world you go to from the present one, then A is true at all of them. So, I mean, you can also say that in fact it's an equivalence that box A is the same as not diamond not A. So it's also to kind of say that there's no world that is reachable from the current one where A is false. But here's the direct interpretation. It says, for all accessible worlds, W prime, and by accessible, again, we mean that R W W prime holds. So for all W prime, such that W prime is accessible from W, then A is true at W prime. So this is just to say that A is true at all worlds accessible from W sorry, from W. Okay, so then, just as in propositional logic and first-order logic, we have notions of validity and of satisfiability. So, like in first-order logic, we have the notion of being valid relative to some choice of frame, which is like being valid relative to some choice of first-order structure. And then we'd have the idea of just being valid, which means that it's valid in all possible frames. So A is valid in the frame M, and so if that's the case, we drop the valuation and the world, and it means that M and W and rho satisfy A for all possible valuations for the frame and all possible choices of world W. So a formula is valid in a frame if it is true under every possible valuation and at all possible worlds in that frame. And the formula is simply valid if it's valid in any frame. So in other words, no matter which set of possible worlds and which accessibility relation we take, then the formula always turns out to be valid in that frame. And similarly, a formula is said to be satisfiable in a frame if at least there is some way of making it true. So there is some valuation, rho, and there is some world in the frame where under that valuation, A is true at the world. So M, W, and rho satisfy A for some possible W and some possible rho. And a formula is just satisfiable if you can at least find some frame where it is satisfiable. So you can find some set of possible worlds and some possible relation such that at least one point in the world it becomes true. Just as in first order logic, you can kind of turn this around and say that if a formula is valid, then it is valid in any particular frame that you might pick, almost by definition. If it's valid in any frame that you pick, then it's certainly satisfiable in that same frame that you pick. And if it's satisfiable in some frame, then by definition it's satisfiable as well. Okay, so here on the whiteboard, I've slightly modified my my previous frame. I've made two changes. First of all, I've removed the edge from the chair to itself. I've decided that that you can't stay in your chair. If you're in the chair, you can't stay in the chair because not with all the the tapping that's going on, and you can't go from the door to the window directly or from the window to the door directly. So I've deleted these two edges as well. This is just to make the example a little bit more interesting, and then we can think about which kind of formulas involving modalities are true at which particular states. So, for example, if we think about the state chair, well, the proposition R for Raven is not true there. The Raven's not in the chair, it's at the window. That's the only place where R is true. But definitely at the world chair, the formula diamond R is definitely true because there is at least one world, window, which is accessible from the world chair and at which the formula R is true. By the way, I'm not writing the the frame or the valuation as I would in the full satisfaction relation because I've already chosen my frame and valuation. So I just have world satisfies formula. And that makes sense because I've chosen my frame and valuation. You can also see, by the way, that that it's also possible to access a state door from chair where R is not true. So also so the state chair actually satisfies diamond R and diamond not R. So it's possible that Raven and it's possible that not Raven, if you want to think of it that way. We could also think of a box formula. So if you're in the state or the world chair, then the proposition T for tapping is not true there. But because you no longer have the option of staying in the chair, it is the case that for any state you can get to from chair, which now does not include itself, so whether you go to the door or to the window, there is tapping. So this means that since the proposition T is at all the accessible states from chair, chair satisfies the formula box T. Okay. So we can also think of, let's think now about, so obviously these formulas are satisfiable because they're true at some world, and you could also think of what kind of propositions are true or what formulas are true at the world door or at the world window. Let's think about a formula that is valid in this frame and relative to this valuation. So I mean, of course, validity in a frame really means validity for all possible valuations. But let's just observe something that is true of all states, which I'm going to write here. For this particular valuation. So the formula the formula R is not true at all states. The formula diamond R is not true at all states because it's not true, for example, at door. Because the state door and chair are both accessible, are the only ones accessible from door, and R is not true at either of them. But actually, it is true that diamond R is true at all three states. So it is true at door because it is possible to find accessible state chair, from which it is possible to find another accessible state R, another possible accessible state window where R is true. So we can also, by the way, label this and kind of remember, if you like, that diamond R is true at chair. So diamond R is true at door because there is a state chair that is accessible from door where diamond R is true. Also, diamond R is true at window. Why? Because there is a state accessible from window, namely itself, where R is true. And that also means that not only diamond R is true, but diamond R is true at window because I can go to a state, namely window itself, where diamond R is true. So because we can go from window to itself any number of times, we know that R is true, and so is diamond R, and so is diamond R. And that means, for the same reason, diamond R is true here and here. So diamond R is an example of a formula which is true at every point in this frame. Okay, so let's go back to the slides for one final time and do a little piece of reasoning about not just validity in a particular frame, but just validity, in other words, validity in any frame. Alright, so to finish off for today, let's consider how one might prove the validity in any frame of particular modal logic formulas. So here's a lemma which says that the formula box A and box A implies box B is valid. So this formula says that if A is true at all accessible worlds and A implies B is true at all accessible worlds, then B is true at all accessible worlds. So if necessarily A and necessarily A implies B, then necessarily B. Now, actually, I think even from that kind of that statement, at least about accessible worlds, you kind of get an idea for why it might be true. Now, let's see how one would construct like a proper mathematical proof of that fact. So, if we want to show that it is that a formula is valid, it has to be valid in all frames. And so let's just pick an arbitrary frame, and we're not going to assume anything about it other than it is a frame. So we'll pick an arbitrary frame, nothing special about it, and we'll call that M, with worlds W and relation R. Now, we have to show then that the formula is valid in that arbitrary frame. To show that it is valid in that frame, we have to show that it is true under all possible valuations for the frame and at all possible worlds in the frame. So, to that end, let us pick an arbitrary valuation rho. Again, we will assume nothing about that valuation. And we'll pick an arbitrary world W in the frame. And we won't assume anything about that either. If you can prove something for arbitrary choices of world valuation and frame, then you know that it is true for all worlds, valuations, and frames. So what we have to show is that the formula in this lemma is true at the arbitrary chosen world W in the arbitrarily chosen frame M and under the arbitrarily chosen valuation rho. So we have to show that this formula is true at world W in the frame. Now, that means what we have to show is at the top level is an implication. That means we assume that the left-hand side of the implication is true at world W, and we show that the right-hand side of the implication is true at world W. So, as I've said before, we never care about the case where the left-hand side of an implication is false. We only care about about the case where the left-hand side of the implication is true, which means to prove an implication, you always assume the left-hand side and prove the right-hand side. That's standard proof technique. So let's assume that the formula box A, which is the first conjunct, we'll assume box A is true at W, and we'll assume that box A implies B is true at W. And I'll call those facts fact 1 and fact 2. This is good practice, by the way, if you ever want to refer back to things. And what we have to show, required to prove RTP, is that then the formula box B is true at W. Okay, so we have we have two box formulas that are true at W, and we have to show that a third box formula is true at W. So we have to go back to the definition of the satisfaction relation and kind of check that. Now, just remember that to show box B means we have to show that for all worlds accessible from W, then B holds at those accessible worlds. So let's assume some arbitrary accessible world W prime. So we know that W prime is accessible, so RW W prime, but we won't assume anything else about W prime. It has to be an arbitrary choice because we want to show it for all accessible worlds. And we want to show that if W prime is accessible from W, then the formula B must hold there. So we'll assume RW W prime, and we have to now to show that W prime satisfies B. Now, the formula box A, we know that that is true at W, and that means for all worlds accessible from W, the formula A is true. So in other words, since W prime we have assumed is accessible from W, that means that the formula A must be true at W prime. So just from the fact that W prime is assumed to be an accessible world, and the fact that box A is true at W, this means that W prime must then satisfy A. And by exactly the same reasoning, but this time using assumption number 2, we also have that A implies B is true at W prime. Now, since A and A implies B are both true at W prime, then it must be the case that W prime satisfies B. We know that just from the truth tables or propositional laws. If A is true somewhere and A implies B is true somewhere, then of course B must be true as well. And that's exactly what we wanted to show. We've shown that W prime satisfies B, which, because the choice of W prime was arbitrary, means that box B is true at W, and that's exactly what we wanted to prove. We assumed the left-hand side of the implication, and we showed the right-hand side. So here we've done we've done a certain amount of backwards reasoning and a certain amount of forwards reasoning. So we've kind of broken down the goal. We said what we had to prove. We broke down the goal some more, And then we got some assumptions and worked kind of forwards. So we've done a combination of going backwards and forwards, and that's very typical for how you want to approach a lot of proofs. And that brings us to the end of today's lecture. Next time, I think we're going to talk about some interesting equivalences that hold in modal logic. And we're also going to see how modal logic formulas can capture various kinds of conditions or restrictions on the accessibility relations in frames. So I shall look forward to that. I hope you do too. Thank you for listening, and I will see you again next time, and take care.